Hey guys, what's up? Eddie Aho here with KissAnalog.com and the Active Power Factor Correction Circuits. So what do you guys think of that circuit? We're going to jump in, look at the board design. So if you didn't see the last couple videos on the 1000-watt converter, which is a scaled up version of this one, I talked about scaling, how you can scale things, come up with the value for an inductor, come up with the switching frequency to change. Maybe you want more power, less power, and you want the same inductor, so you can change the frequency to do that. You can just scale things. So talked about that in previous videos. Watch the playlist on that, okay? And yeah, I went into a bunch of different things on detail on a PFC converter, which, if you really know one converter, it really helps you to learn other converters, I think. So let's jump into the board design, okay? Now, guys, what we've done so far is we reviewed the schematic, and before that, we actually just kind of looked to see how the 1000-watt converter test report looked. The efficiencies, all that, and the reasons why we might like it. And then we reviewed the schematic in a previous video. This time we're going to take a deep dive into the board. Okay, so let me know what you guys think. Let's do it. All right, here's a board. All right, look at this. You can see the silk screen. So I can see them up here. Okay, that's as close as it'll let me zoom in. So it looks like, and look at this, the silk screen is, well, it's almost right. A lot of it's right. It still looks like there's things that are upside down, wrong way over here, and over here on the left side. It's inconsistent. The capacitor identifier is up on top here. Over here it's on the bottom, so it's right next to the fuse one. It'd be nice if it was up on top so it's consistent, so you know where to find things. The inductors, it's kind of hard to tell. Yeah. Anyway, guys, and then the capacitors for these two. This one's slightly to the right, so does that go with this capacitor and this one go with the left one? I'm not sure. Why not put this right on top of this one? Why not put that reference designator right on top of that one? I mean, why don't we make these things easy to read? Guys, when you design a board, you only have to spend a few minutes to do this stuff, and it makes it easy for everyone after. Okay, let's look at up here. I'm zooming. Okay, this capacitor's, backwards, right? Well, unless you're reading, well, okay. So let's say in this case, I'm rotating it to the left. In that case, these three things are correct. So those are good. And is it good all the way across? Look, this guy would be red. This guy would be red. So yeah, if you rotate to the left, it looks like that's the way they did this one. So that works, guys. Someone did a good job. And other than that, the ones horizontal, I think they're all correct, aren't they? None of them are upside down. And I don't think so. I think they all look good. And look at this. On the bottom of them, on top of them, next to them, there's this. And okay, this one's a little bit inconsistent because these two are to the left or to the right, and this one's on top. They could have put them all three on the left, and then they would have been easy to go boom, 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 right? So a little care about what you're doing, a little attention to detail, and you can just make your work not look sloppy. R126 right here, R127's down here. It's, I don't know, it's wandering around. Oh, I think it's supposed to be up here. Why not just put them to the side? Why not just, maybe, I mean, you could put them all to the left, these three to the left side, these two to the left side if you wanted. Maybe in this case, it might make more sense to put them on the right side since we got this via here. All right. You know what? Actually, look at the copper right here. I can point out a few things, okay? So when you just look at the copper and see these traces coming up here and see these planes. Now, this is a big plane shape, right? This big piece of copper here. But I look to see if they're buttoned down, okay? Now, if it goes to the other layer, it should be buttoned to the other layer, so they're sewn together like a quilt on a mat, on a blanket, right? That you want them all quilted together so that they're not flapping around. And when I see this, it goes to the other layer. There's a couple pads here. There's a pad down here in the corner. And then there's a couple of sharp corners here. It's good to get rid of these sharp corners. There's no reason to have them. And you know, this trace, it's a sense, I think, because they're both coming off the same spot. They're coming this way. So that's the kind of thing that is done well. And that's where TI knows what they're doing. And then it's the sloppiness or the loss of our electronics where, like this thing right here, why is this thing come up here? Is it supposed to shield? Well, if it is, why not put a VA here to the other side so that it stitches this down so it's all the same potential. So we don't have a low impedance here to the other side, and over here it's a higher impedance because, and especially this little island here and this sharp corner here, you know, just get rid of that, guys. Just taper it off, make it, or bring this out, make it a nice rounded end. Don't leave these sharp corners. Same thing down here, you get corner, corner, you know, and a corner right here on this thing. People think that looks good and all that, and it's easy on your tools because your tools, you just say have a keep away and you put this plane shape down, and then the tools push things back. But then you go in and fix this stuff. You don't just be lazy and leave it there, okay? EMI, now you're making eval cards, you don't care. Okay, fine. Now look at this point right here where I'm circling. Look how this flat layer comes so close to this, especially in eval where maybe somebody's going to solder another part. Why have that so close? You know, I mean, and then why have this big gap here? It's nice to have the gaps. You don't want things, you know, conducting across, especially a switching node. This looks like it might be a switching node, but in that case, that's even more reason. Why come close here? Pull that back away from there. Like maybe have this drop down slightly, but pull it away from there. Don't let those things come close like that. That's just bad. That's bad, 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 guys. Okay, your heat sink's mounted here. I think it looks like it's mounted here. It's mounted here. So remember, it's tied to that return spot, but then it's not you know, it's not touching here. But if this is live now, the same potential as this, then see the gap between these two things? You'd want the same gap between them, at least, because that screw could move around, right? So I think that just feels like that should have a bigger gap there. And on this end here, you got some traces running next to this. You know, same kind of thing. If you can move all that copper to the left a little bit, just get it away from this screw, might be fine, might be totally fine. But since it's an eval card and somebody might remove these heat sinks and move things around, up here on the left, the other heat sink looks like this guy is fine, this guy's fine, this guy's fine. Nothing's gonna be, you know, if it's moving around and stuff, it's not gonna touch anything. Now, going back to the top, the only thing I would say is I would take all three of these resistors, scooch them down just a little bit, say 10, 20 mils, because these are kind of ceramic, they're just, you know, a little bit, anyway, you're putting tension on the board here. Just get it away from that big resistor, especially since he's physically large. Just move all three of them down this way a little bit. And in fact, maybe even put a little bit bigger gap between them. And you see these vias taking this plane to the other side. Take these vias, same thing, take them up higher, just like this one. You kept it away because of that screw, but that screw's touching this thing, so it doesn't matter, right? So bring those vias up a little bit higher, bring these resistors down, okay? Now this is our little township over here, nice quiet ground around it, right? That's that analog ground, everything's nice and tight. That looks good, right? But it's going to wrap around, and where's it going to, I'm just wondering where it actually gets to ground. So you have to follow this to see what path it finally gets to ground. But it is, see, it's that nice quiet analog ground, you know, that's around there. So that's nice to see. All right, let's go back to the actual Gerber files. All right, guys, let's go down here. Now, here you could look at the drill files and stuff. One thing is these keep out regions around these holes. Well, I don't know if copper's flowing. Here, I guess we got to look. maybe where I see dark is where the copper is. Yeah, that, I don't know. Let's scroll down here and take a look. Okay, let's see how this power comes in. Okay, guys, remember we have a fuse here, okay? All right, I'm going to refer to this drawing. I'm going to jump from that drawing to this drawing, but right now let's just think about this left side. Here's a power plug, okay? IEC connector. Fuse to the left, so it comes up, you can see it's on some copper here, okay? Here's our Y caps, here's our X cap, and here's our ceramic and an MOV and that relay. So let's look at this part right up to that first common mode choke. All right, so we have our fuse from here to here. So from this piece copper, so this is our power coming in. So it's these three holes right here, I guess. So this is line on the left, ground here. It comes up to this plane with two connections, and that's those two Y caps, one to the right, one to the left. Okay, that connects to this ground. Fine, that's great. There's our Y caps going to ground. Okay, fuse comes in here, connect to our line, jumps over here, so now this becomes our line, okay? So this big plane's our line. One of those caps is tied to the line, coming over here to the chassis ground. And then we have this one down here, which I have to go back to look to see what that is. All right, that's got to be this X cap. Okay, that's the X cap, comes across here. So X cap across here. So Y caps across the top, X cap across here, and then our input breaker here, and then we have a hole here that's just a mounting hole, I guess. And so we have several holes. So this is that breaker. You know, breakers are always interesting hole patterns on the bottom right, but let's see what is going on. So see that hole right here? Let's go down here and see where that hole comes in. Okay. That hole is this guy right here, and it comes over here. So you know what? I think I know what that is. So we have a hole here, and then the copper comes up and connects to there, okay? So it connects to this spot. So it's basically connected to the line side. So you know what that is? That's that MOV, right? That's the MOV tied across the line to neutral. Here's the neutral over on this side. It comes up here, it connects to, you know, a few things up here. Okay, it goes to that breaker. Now, to get to this copper plane, we come across that, I think we come across that white resistor. See, here's that white resistor right here. Here's that MOV right here. So that's how it's tied to from here to the fuse side to this side. So if that MOV goes off, hopefully it pulls off fuse. But guys, that's another whole story. This MOV, bad idea to put these in the circuit unless you know what you're doing. It's just a fire waiting to happen. And it's real small, so what good's it going to do? And look, do you want a fire next to all this stuff? I don't think so. All right, so we have our resistor, and then our breaker must, you know, short one of these pins together, who knows, but our resistor's right there. The breaker's probably tying these two pins together or something. Maybe it's tying the two pins from here to here. I'm not sure, but somehow it's shorting out that resistor. Okay, so the breaker's tied over here and to here, and that ties that. Okay, so then now we have neutral coming up to this point, and we have line coming over to this point. And then we have these two guys and these two guys. That's going to be that common mode choke, right? And if we come up here, we see it goes to these two copper things. And then look, up here, same kind of thing. So these are the two common mode chokes, I'm sure of it. But underneath here, we have something that goes over here to Y cap. And then over here, we have something that goes to Y cap. So this is usually a bad idea, guys. Underneath the common mode choke, we have a coil here on this side, coil on this side. Well, this coil on this side was trying to choke the common mode noise on this side and equate it to this. You know, there is common mode, right? So the same noise is hitting both sides. But now we're kind of coming across these windings on the inductor, and we're bringing a kind of a winding across here to chassis. And it's in series with this guy, right? So it's coming across, going through these caps and coming through here. So we're creating a field from this guy around around the combo choke, right underneath the combo choke. So it's usually not a good idea. Usually you want to keep the field underneath the combo choke blank. Look over here. We're taking the power off the combo choke. We're backing up. We're going right back up underneath the combo choke. Oh, don't. Nothing going on here, guys. Yeah, don't worry about conducting anything, emanating any noise. There's no magnetic field coupling or electric field coupling here. Nothing to look at. And then we're just going to come over here and bring power here. So our line power come up here. Now it's come over here. Okay, now it's connected to these two things, our bridge rectifier. And this guy's connected here, and I'm sure he's connected here. Let's go look at the other layer. Yep, look at this. Here's our bridge rectifier on this layer, and here's the bridge rectifier on this side. Okay, so this guy perfectly fine wraps around the EMI filter and comes this way. Guys, usually through the center of the EMI filter, you don't want to have any copper crossing like you did here. Like this guy here crossing over. Yeah, don't look at me. Nothing going on here. I'm just taking this white cap stuff, and I got to take the white cap stuff here down to here. Just got to get it there somehow. So yeah, it would have been better to go a longer route down to here and back to the ground. Just come around it, guys. Don't cross over the filter that you just put chokes in there to choke out that stuff. All right, so then once we get the bridge rectifier, guys, on this side, it's going to be basically pulsating DC, right? So, and you can see the heat sink is connected, all 3 points right across here. So, okay, that's fine. Not too many sharp points. There's kind of one here, but whatever. I mean, essentially looking pretty good. Okay, so we got this big copper plane bringing power this way, and that's from the bridge rectifier pin 1 here, and pin 4 here, and pin 4 down here looks like. So down here we got, what is that one? Is this one? Yeah, so we got this connection here, and then we have this guy going all the way down here. Okay, now see this guy here? He's tying this, right? It's just one bridge rectifier, so I'm wondering how the other current from the bridge rectifier gets down to here. So see that stitch right there? He's stitching himself to this one. So that's how, so these two guys are stitched together, okay? And then the other power from the bridge rectifier comes this way, okay? Okay, then over on this side, remember how I said that stitching should go all the way up? The reason it didn't is because, look, we have a couple traces there. Now these traces are running real close to this, so that might not be a good idea depending on the fields that we don't want conducting, radiating and magnetically coupling from here to that one. Because when you hug something that close, you're bound to couple into that one. So, and there's space, it might be good to move both those traces to to up, away from this pattern here. Now this pattern might end up being ground because look, it comes down to the output terminal. So that's ground. So maybe that's good. Maybe that's a good place to couple it to. So we come down here and we see the ground terminals here on the output, and this is the plus output. Okay, so look at this. We're pulling from this via field, and look how sharp this thing is down here, by the way, guys. This is super sharp. You don't want sharp things like that because you get eddy currents and you get EMI. It's like, yeah, I see a lot of corners, like these corners down here. Just get away from this feature. What gets us so island, this so feature that blows up right here that creates this corner? And then we got this sharp corner here, like, man, holy cow, like smooth that stuff out. Same with the top piece. And then look up here, there's this real sharp corner on this pad. It's because this plane cut through the pad and left a corner of the pad free. That is not a good thing, guys. What you do is you come down here, connect to the top of that pad, come up to the top and then down. Capture that whole pad so you don't have this sharp corner. That's not a good thing. And same thing here. This plane shape came down, just barely touched this pad. You know, to the top of that, bring it a little bit higher and come down and capture that whole thing. Like, why isn't there any copper right in this space here? Why didn't this come down as soon as we pass by all this stuff, bring it over here and couple? Like, that makes no sense to me. Yeah, and then, okay. So guys, looking up here, this is our big inductor, okay? Okay, this is our big inductor. So the voltage comes through here, it goes to the top of the inductor. The bottom inductor is going to go through the FETs, get switched on and off, right? And then when the FETs are off, then the current from here is going to go through a diode to the capacitors. And when the FETs are on, it's going to just pull current from this guy down to ground. He's going to charge them up, right? Okay, so let's go look at that again. And then you see the 3 caps here, okay? And you can see why they're offset. It's too bad they're touching the heat sinks, you know, because you don't want to get these caps hot. But if the board was just a little bit longer, then these could have been straightened out so they weren't touching the heat sinks. But yeah, it's too bad that it was designed that way. It's almost like if this inductor had been set on an angle right here, then maybe you could have straightened out these capacitors. But that's bad design. And then having this capacitor sitting right next to the heatsink, again, bad design. That capacitor should be pulled to the right a little bit, okay? All right, so we come back up here, the inductor, one side of it, the voltage comes from the rectifiers up here to the diode, right? They come up to the inductor right here, right? And then the other side of the inductor is tied to this little island. Look at this big old thing. And then this little island right here, tied to the 2 transistors are going to switch on and off. This is a switching node. The switching node, you don't want a big old trampoline putting out emitting noise, but at the same time, you want low impedance. So you want the impedance from this inductor to that FET and to this FET the same. It doesn't look like it is, right? This is a big old bulk copper right through here, and it's a long skinny highway down this guy. So I think what should have happened is this little pencil here should have started opening up out here and came and filled in this region here. So, and then this guy up here on the top, what's the point of having that so thick when you got this little thing? So shave off this corner, which shouldn't be there anyway. From this point, just come right over here like this, and maybe come down a little bit because you got this necking here. But still, look at the necking you got on this little dude. Let's think about the switching node here. So from this guy, he should be pulled away from here a little bit and made this bigger so you get more current instead of just off this little piece of, you know, from the lead to these little, I mean, guy, basically one side of that lead is connected to this trace. So pull this open, put a bigger pad here, run it down, you know, make this area through here thicker. And then over on this little strip here, same kind of thing. You could make, on the bottom part, you could open it up and make this angle down this way. And then also the same thing, put more copper around the pin, okay? Make it a better connection to that. Kind of like the one over here on the bottom right. It's a little bit better, right? It's thicker all the way around it. It's big, thick thing coming down to it. And then this guy further away from these 2 guys, it doesn't have the same impedance. So if you want this parallel action going on, come on, man, let's work on that. The other thing is the bottom transistor, you see this nice island with all these vias? On the top one, big island, bunch of vias. So if it's big enough, it's big enough, you know. But again, why this goofy shape right here? Bring this island straight down, make this thing a little bit bigger around this pin. And then here's the gate drive, guys. This little thing here, little trace. I don't know what that is, 8-10 mil trace. Make that a 20 mil. Come on, low impedance to the gate. And where's the gate resistor? How come the gate resistor is way over here? Then we come over to this guy and look at this one. It's got a closer connection. That's great. But look at these 2 big traces come down here and then they break off in these little things. Come on, man. Make these traces a little bit thicker. You put a gate drive chip in there, right? You put two transistor totem pole because you're worried about driving these things. Well, for hell's sakes, let's put a little copper on the gate drive pins. Okay, that's just craziness. And this teeny little trace here, that is just, these traces need to be bigger. Low impedance. We don't care how much current they're handling. We want low impedance. Okay? Anyway, holy crap. Now, I'm only assuming over here on the bottom left where I'm circling is voltage feedback coming down, running around, coming up, and going up this way. Okay? And, that all looks fine. This is ground down in here on the bottom, so I think it's fine that it travels around ground. But yeah, so that to me looks like it's probably voltage feedback. Okay. Now, hold on. Let's go look at those current sense resistors. Let's see where they are. Maybe they're right here. Okay. They're not on that side of the board. Oh, here they are. They're right underneath. So remember, the control IC is right here, and then the current, and then we have the heat sink, the pads right through here. And then the current sense resistors next on the other side of the mounting hose. So the current sense resistors, see where the inductor is? They're really close. So the current sense resistors are going to be between the mounting hole and the inductor. Okay, so here's the mounting holes and the inductors right here. So current sense resistors have to be strapped right here, guys. Right across these two fields. And it's nice they put these vias on both sides to stitch them to, okay, yeah, here they are right here. Okay, that's what they look like, the pads. Okay, so then we come back up here, we see them. Let's go to the other layer. There they are again. Now look, current sense, we have, here's a Kelvin pickup. These two things coming up here for current sense. Nice job. That looks good, guys. I mean, what can I say? That looks like a good job. Now, the current sense resistor is going to get hot, and it might have worked better to bring the copper in a little bit closer. You could have had the Kelvin connection come up and then come straight in and then tee off. And so you could have brought this pad up here. So maybe where this copper is here, it could have come straight out, right? And then down. That would have given more thermal and a better connection where the current's rushing through these things, and then brought these two guys. What I was thinking is, this is switching current. You don't want to create noise here, but at the same time you want to pick up a Kelvin connection. So you could have maybe, I think it would work just as well to keep them out of the current path that's going across this way, and just did the Kelvin connections right here at the top, right here at the corners. I mean, what's the difference of here versus here, except for the current that's traveling across the resistors, conducting magnetic field, electric field, whatever, any kind of noise into these two traces. So I think backing them off a little bit, bringing this pad up higher, getting lower impedance across those resistors, would have made the Kelvin connections better, I think. So good job. Maybe not as great as it could have been. Okay, now looking over here without knowing what these traces are, it looks like they're coming off of these two things. Maybe they work together. If they don't, keep them away from each other. Don't bring them next to each other just because you have two traces run. See over here on the right how they kept these guys away from each other? Same thing with these two guys. In some places, these guys did a good job. In other places, they're a little bit sloppy. So looking right here, just a lot of teeny little traces, guys. Copper's free. Remember, copper's free. It comes on the board. You take it off. So this little trace right here, here's a mounting hole. Running that close to that, why? Back it off. Just get it away from it, okay? You got plenty of place to put copper. You don't need it next to this mounting hole. And what's the point of circling a mounting hole like that, guys? What's the point? You don't want to conduct a field off of it, right? So just avoid the damn thing. Just cut it away from it, okay? There's no sense in putting, when you're trying, yeah, there's just, it doesn't do any good. Look at the sharp edges over here on the right one caused by that. It's just, it's an easy, kind of lazy way to do it. Let the tool back off the copper away from holes, but come over and clean them up. You can put plane shapes down. You can clean this stuff up so you don't have sharp edges. It's an eval card. Show off and show how to do things right. Okay? Did a good job, just not a great job. Okay. I think that's probably good, huh? I go on and on with this kind of stuff, but right angle connections like this, this is an EMI connection, right? Just again, picking things apart. This is just silliness. Yeah, why? It's what you want common mode, same noise on both sides. You want the same impedance, same value of Y caps, all that. Why run the trace like this? Laziness. Run a trace between the two pads, put a V shape there, and take this pad. This should be a low impedance. I mean, you put these Y caps, low ESR caps, and then you put a trace. For hell's sakes, this should be a plane shape right here. If you're going to do traces, do wide traces. Do wider than this, and don't angle this way. It's EMI. Why are you making corners? This guy should have a trace from this hole straight to this one. This MOV, get rid of it. Doesn't do you any good. It's fire hazard. If you are going to put it there, rotate it. Move it out of the way if it's in your way. But make this thing shoot straight up in the middle of that. Make those equal impedance, low impedance. I'd put a plane shape here, maybe a pyramid shape here connected to a big trace to this thing. And make the trace, make a nice plane shape around this pad here. So it's not just this little trace coming off of it. These guys here, same kind of thing. Ridiculous to come here, turn left. Why are you making right angles in EMI? This should be a straight shot to that pad. And in fact, it should be a big plane shape. But the problem is, I mean, yeah, from here to here, that connection is fine because your combo chokes are over here. So make a big old plane shape to that thing. But the placement of these things is done badly. Those two Y caps should have been here. They should have came down here connected to these Y caps to these. It should have been straight down the middle. You shouldn't be crossing over your stuff. And the only reason you do this kind of thing is if you're running a chassis connection around the outside down to here. Okay, doing it this way. So somebody saw that putting them over here makes sense. Oh, that's a good place to put them. But that's because they're routed different. You don't route a trace like this for EMI. That's like taking your through hole part and just making one lead really long and the other lead short. Does that make sense? No, doesn't make sense. So don't do it. Plane shapes. Put Y caps right here on both sides, just like you did down here. Connect them just like you did here, and get a combo choke with wider pins. Those are teeny combo chokes. Okay. Yeah, but put the trace right. Put it on the opposite side of the board. Connect them straight down. Okay. Look at this. You could have put them on this side. You could have. These parts here don't have to be there. They could be somewhere else. The EMI parts are essential. Hey guys, so what do you think? Yeah, routing, placement reviews. All these reviews are very important. So, yeah, hopefully you guys learned something. I had, good luck doing board design. So I think it just takes some attention to detail. Signal integrity is a big deal. Power integrity is a big deal. So yeah, hopefully you guys learn. If you guys have learned things, let me know. EMI stuff I'm always looking at, like the EMI specialists, like what they say on how to route this and how to route that. I see some things I agree with, some things I don't, but I learn a lot. So I watch a lot of that stuff, and yeah, interested in what you guys know. Okay, so yeah, please share. We may not always agree on everything for certain reasons. We've had our own experiences or whatever, but always good to hear and bounce it off each other, right? So feel free, don't worry about saying the wrong thing in the comments. Just let's share, okay? Thanks for watching, guys. 2 big thumbs up to my members of my YouTube channel, Danny for being a team member, and my patrons. Appreciate you guys. Subscribe if you haven't done so. Look, check out the playlist on these PFC converters. I've got lots of information. I tried to attack it in different ways to kind of jump into the inductor and looking at it in different ways to give you a good feel for how that inductor is designed and the size of it, that kind of thing. The scaling principles of how you can scale frequency, power, all that stuff to get to use one design and to come up with a new design just by scaling. Okay, so yeah, what do you guys think? Let me know what you think of this. We're going to get our own board designed. I'm going to show you some Gerber files. We're going to go through that, and we're going to jump in and try to come up with our own board. Well, we will come up with our own board. I've kind of narrowed down the board houses to a couple, I think. So yeah, there we go. Thanks for watching, guys. We'll see you next time.